ಇಲ್ಲ ಮೇಡಮ್ ಮೀಟಿಂಗ್ 11 ಮೀಟಿಂಗ್ ಜೊತೆಗೆ ಮೀಟಿಂಗ್ ಅಂತಾರೆ
ಇಲ್ಲಿ ಬರ್ತಾರೆ.
ಮತ್ತೆ
ನಂಬರ್ ಆಫ್ ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ ಅಂತ ತೋರಿಸಲ್ಲ ಅಲ್ಲ ಅದು
ಇದೆ 11 ವರ್ಚುವಲ್ ಟಾಕ್ BIC DVCs ಲೈವ್
ಮಾತಾಡೋದ
ಲೈವ್ ಹಲೋ ಅಂತ
ಹಲೋ
Hello.
Raghunandan, are you hearing me?
Yeah, tell me.
Yes. So we'll start the virtual session now. So
Okay.
good morning to each and everyone who have joined the virtual talk on computer organization and architecture. So a dream written down with a date becomes a goal. A goal broken down into steps becomes a plan. A plan backed by action makes your dream come true. So good morning, everyone. Today, we are conducting a virtual talk on computer organization and architecture for second year BCA students. So, it's my immense pleasure to welcome our speaker, Mr. Raghunandan GH, Assistant Professor, Department of Electronics and Telecommunication from BMS Institute of Technology and Management, Bengaluru. I welcome Mr. Raghunandan GH on behalf of Bapuji Institute of High Tech Education. I welcome you, Raghunandan, sir.
Thank you, ma'am.
Okay, I would also like to welcome our second year BCA students to this virtual session, and also I would like to welcome all the faculty members who has joined this virtual talk on computer organization and architecture. Okay, so speaker Raghunandan GH has a work experience of 10 years, and he is an assistant professor in the Department of Electronics and Telecommunication at BMS Institute of Technology and Management, Bengaluru, and also he is working as a deputy placement officer in the same institute. He has received a Best Professor for Electronics and Communication Engineering Award by Karnataka Educational Awards 2018, held on 20th December 2018 at Bharatiya Vidya Bhavan, Bengaluru. And he has also won Best Paper Award for the research paper, which was presented in DRDO CSIR sponsored 9th Conference on Control and Instrumentation System 2012, held at Manipal Institute of Technology. He is also serving as a reviewer for Springer's Eurasip Journal on Wireless Communications and Networking since July 2018, London, United Kingdom. So I'll over to Mr. Raghunandan GH to continue the virtual talk on computer organization and architecture.
Thank you, ma'am, for the brief introduction. Is the screen?
So now over to Raghunandan.
Yeah, is the screen visible, ma'am?
Yeah, it is visible.
Okay. Good morning, one and all present here for the online session. So, thanks for the brief introduction. So, I work for BMS IT as a assistant professor as well as a deputy placement officer. So, today I'm here to give a brief overview and to share some knowledge about computer organization and architecture. So, more or instead of going on with thorough in the syllabus, what you listen in your classes. So today I would like to give an overview about CO and architecture. Are they same? Are they different? Or if they are same, how they are same? Or do they have any relation? What is that relation? So among computer organization and architecture, which should be chosen first, and what is the importance of that? So this kind of questions, we should be clear about that because you guys are going to be bachelor, you'll be holding a bachelor degree in computer applications. So computer organization and architecture becomes a basic knowledge that everyone should pursue. So why we study computer organization and architecture? That is the first question that comes to our mind. So basically, to design, optimize, evaluate, and understand. What to design? To design better programs, including system softwares such as compilers, operating systems, drivers. So to design all these things, we should know, or from this computer organization, we will get a better knowledge to do this task. Next, optimize the program behavior. See, whatever the programming or whatever the design or whatever the task we do, we looking for optimization or optimum to the optimum level. So to optimize the program behavior, we how to optimize it. All those things we are going to study in computer organization and architecture. Next, evaluate the computer system performance. See, if you want to tell some system is working fine and it's the best, or it is it is one of the best computer we are having. So there should be some benchmark. If it is crossing that benchmark, then only we can tell that is the best computer. So in order to evaluate the computer system performance, we are going to how to evaluate it, that we are going to study in this. Next, to understand the time, space, price trade-off, all these things, to understand what is the importance of time, space, price trade-off in computer system. So we are going to study this. Now, basically, computer organization and computer architecture, these are two separate. There are two huge subjects, separate subjects. So, because of the time constraint in our semester scheme, they have clubbed into computer organization and architecture. So, let us now try to know what is this computer organization and architecture. The computer organization, it deals with the physical aspect of the computer system, like we have a circuit, motherboard, all those things inside the computer system. So what kind of the motherboard I need to choose, and how actually what kind of memory types I need to use, how I need to integrate them, connect them. And finally, computer organization deals with telling how does a computer should work. So how your computer is going to work. So based on that will be discussed in computer organization. As the name itself tells, computer organization. So how you are going to organize, how you are going to choose different the components required to build your system. So that we are going to study in the computer organization. Coming to computer architecture, so basically it deals with the logical aspects that which is mainly seen by the programmer. So here examples are the instruction sets, instruction formats, data types, addressing modes. So these are the things where the computer architecture comes into picture. So I can tell, it is going to tell you how do I design a computer. So first we need to design a computer. So we have some uh, already some requirements requirements. So based on that requirement, we are going to design a computer. So how do I design it? On what basis I need to design? So all those things we are going to study in the computer architecture. So now we can think which is the first, whether computer architecture is the first thing that we should think, or computer organization is the one that we that comes first. So, in my knowledge and in actual scenario, computer architecture is the first. Based on computer architecture only, the organization can be done. The organization can be done only when the design is ready. So that design is done by architecture. So let us try to compare these two aspects. So computer architecture and computer organization. So computer architecture, it is mainly concerned with the way the hardware components are connected together to form the computer system. So the way See, it is not telling about hardware components. They are just concerned with the way how you are connected. Based on that, you can program it. But when it comes to organization, it is concerned with the structure and behavior of the computer system as seen by the user. So what kind of the physical components I need? So that will deal in the computer organization. So now computer architecture, it behaves as an interface between hardware and software. So that is where the programmer plays. So in computer organization, it deals with the computer components of connection in a system. So basically, we can tell it is physical, this is logical. Architecture is logical, organization is physical. Computer architecture helps us to understand the functionalities of a system. So whereas computer organization tells how exactly all the units in the systems are arranged. Arranged means organized and interconnected. Next, the programmer can view architecture in terms of instructions, addressing modes, and registers, whereas organization express the realization of the architecture. So that the implementation of the architecture is done by organization. While designing a computer system, architecture is considered first. That's what I was telling. So based upon your application, based upon your requirement, we design the architecture, we plan the architecture. After that, an organization is done on the basis of architecture. So based upon the availability, what kind of architecture you are using, based on that, we are going to organize and form a system. So computer architecture deals with high level design issues, whereas organization, it deals with low level design issues. Architecture involves logic, whereas architecture involves logic, whereas organization involves physical component. That's why I told architecture is logical, computer organization is physical. It deals with physical components, circuits, adders, peripherals, all those things. But whereas architecture, it means will deal with programming, instruction sets, addressing modes, all those things. So first, let us see what is this computer architecture. So in the modern aspects, modern meaning of the term computer architecture covers the three aspects of computer design. First thing is instruction set architecture, ISA. Second one is computer organization, and third one is computer organization, computer hardware. These are the three aspects a modern meaning of a term computer architecture means. So ISA, so instruction set architecture refers the actual programmer visible machine interface such as instruction set, the same thing, instruction set, register, memory organization, interrupt handling, all these things will be taken care here. So one can think ISA is an hardware functionality of a given computer. So ISA is an hardware functionality. Next, task of a computer architect. So if you want to become a computer architect, then what will be your task? So computer architect must design a computer to meet the functional requirement as well as price, power, performance goal. These are the things that should be kept in mind. So that is the importance of this subject. You will learn. So what are the important aspects one should consider? So often they have to determine what functional requirements are and which are the major tasks. So there will be a lot of tasks involved in it, but we should pinpoint the major tasks which are involved. So once a functional requirement has been established, so he has to optimize the design because the design should be always optimum to the optimum level. So there are three major application areas and the main requirements where a computer architect is designated to work. So the first one is desktop computer, what we used in our lab, in our home. Those are desktop computer. They have their little regard to the program size or power consumption. So they are measured by a single user. So this is one application where a computer architect will be working. Next is server computer. So these are mainly focused on the availability, scalability, and throughput, cost, performance. So server computers mainly deal with the interconnecting different computers, maybe on the LAN or maybe on the WAN. So these computers will be used in the network level. So to interconnect different computers. So this is one kind of computer architects can design. The other one is embedded computer. So the embedded computer, these are all application specific computers. So you have some small application has to be done there. There is no need of building, no need of a entire computer setup, no need of a mouse, no need of a keyboard. You just need an application. You just need a LED board which will be displaying some videos and all. So for that you don't need much of the components. You just need some few components which are required for that particular application. So we have seen mainly this kind of embedded computers contain microcontrollers, small microcontrollers like Arduino 8051 microcontrollers. So by using this microcontrollers, we can build embedded computer. So where the application will be specific, it can do only that particular application, but a desktop computer can do any kind of application. So embedded computers are designated or designed for a particular application, like display boards in a bus or a small equipments which we use, electronic equipments which we use in our day-to-day life. So there we'll be using this embedded computers comes into picture. Now, why we learn this stuffs, all this stuffs, computer organization, architecture? Why do we need this? That is the question. Basically, if you want to call yourself as a computer scientist or a computer engineer, you need to know these stuffs. Next, you want to build a software which people use. You want to build some software, you need to build some applications where the people use with a good performance. Obviously, the performance should be there. Without performance, nobody will use it. So to build a software, you need to know this, because you need to know whether the software, whatever you are designing, can run on the system or not. So for that, you need to know this knowledge. You should have this knowledge. Next, you need to make a purchasing decision or offer expert advice. There will be a you will be a computer. You know that a computer dealer knows a lot of stuff compared to uh, a person who has done his degree in computer science, because he is well versed in the that particular field and he knows in and out of that computer. So if you want to know in and out of the computer, you should take this subject or this the organized computer organization and architecture. You should be well versed in this. Then only you can be an expert in that and you can give an expert advice. Someone asks you, "Oh, you have done a BCA. Can you please suggest me a good computer?" So you should know it. What actually he expects? What is his expectation and what I can suggest? So you can do this task only when you are perfect or you are an expert in this particular topics. So now both hardware and software, they are going to affect the performance. That's why we'll based upon our requirement, we are going to purchase a computer. When we go to a shop and we try to get a, computer, so they'll, for giving a quotation, they'll ask, what is your expectation? So the money is the next one. First, they'll be asking you, what is the work you need to do on this? Are you a student? Are you an engineer? Or you are doing some? Are you running a very high end softwares? Or you are looking this computer for gaming purpose, like that. So based upon this, they will come to know. So what kind of configuration can be suggested to you? So because the hardware and software mainly they affect the performance. So you are having a lower end device and you want to play a very higher end game which is having higher end graphics. So obviously it will be slow, and it may not, this computer may not support, because that software is not supporting, or the software and hardware are not matching. They don't interlink each other. So algorithm determines the number of source level statements. Language or the compiler or the architecture determine the machine instructions. The processor memory determines how fast instructions are can execute, and assessing and understanding the performance. So to assess and understand the performance, these things are important. Next, I want someone want to be a um, perfectionist in computer knowledge. He wants to know in and out, not only the hardware part, software, everything, pin to pin. He wants to know that. So during that time, what and all he should know. See, starting from application level, application software, system software, assembly language, machine language, architecture issues like the cache, virtual memory, pipelining, sequential logic, finite state machine, FSMs, combination logic, arithmetic circuits, Boolean logics, transistors used to build these logic gates, that is CMOS, complementary MOS structures, semiconductors made up of silicon used to build this transistor. Again, coming to properties of atoms, electrons, quantum dynamics. If you are perfect with these things, you can become a perfectionist in computer, or you will be knowing in and out of the computer knowledge. See, you are at the first level, application level. Many of them will work on a application level. So obviously they will come, they'll be working till the machine level language or assembly level language. But if you want to know it, basically computer is a combination of hardware and software. See, transistor, semiconductor, properties of atom, these are all the hardware components. So how a chip is going to be manufactured? A chip is going to be manufactured by involving millions and millions of transistor. So how the transistor, when you know how each transistor in one among that million is going to work, then you can analyze how that chip is going to work. So in order to analyze that transistor, you should know that transistor is done. By using semiconductors, the transistor is done. In order to know how the transistor is done, you need to know the properties of atoms, electrons, that you might have studied in your 11th, 12th, or first PU, second PU, Bohr's atomic model, all those things you have studied. So there is so much to learn. There is no end at all. So at least we cannot cover up all those things, but at least we should know the computer organization and architecture level. At least you should have that knowledge if you want to become an computer engineer. So now instruction set architecture. So it's a very important abstraction, because it interfaces between hardware and low level software, because even the interrupt handling or everything is done at this level. So standardizes the instructions, machine language, bit patterns, etc. So the advantages here is the different implementation of same architecture. So you can use the same architecture to implement different applications by using the same architecture. And also true or false, on off, or zeros and ones. These are all comes under the binary compatibility. So that also we need to we will be knowing under instruction set architecture. So the modern instruction set architecture, which are used in IA32, PowerPC, MIPS, Spark, these are all the modern architectures we are having. PowerPC, MIPS, Spark. So these are the modern architecture, instruction set architecture we are using. Now, from the historical perspective, how was everyone knows this? ENIAC was the first general purpose computer which was built in World War II. So This is one basic curiosity everyone knows, and you have googled it enough. So this ENIAC, uh, from that ENIAC to a tiny laptop or a iPad or whatever we are having today. So how this journey was. So what made this compactness that we need to? It's a very quite interesting thing that we need to know. So you can see the ENIAC, which was being discovered by John Markley and Prefer Eckert. So it was built in World War II. So here it was mainly used for uh, artillery firing tables, computing them, and it was 80 feet long by 8.5 feet height and several feet wide. And each of 20 10-digit registers was 2 feet long and used around 18,000 vacuum tubes, performed 1900 additions per second. This was this was how uh, the look of the ENIAC and its performance was. But since then, the Moore's law come into picture. So Moore's law is going to tell more. He's a physicist. So he, after several years of research, he proposed Moore's law, and it's true. And even today, it's working like that only. Since the law is very old, but still, since till today, the same statement or the law, whatever he has given, it is like that only. So he told that the transistor capacity doubles every 18 to 24 months. See, if I take a small board and let us assume today I can place some 100 transistors on that small board. So after 2 years, in the same place, in the same board, I can place some 200 transistors. How it is possible? It is possible because of the miniaturization of the transistor. Because the scaling, everything is scaling down. Previously, we have micro, milli level, milli size. Later on, it came to micro size. Now we are talking about nano. Later on, it is still they are working on a pico level, 10 to the power of minus 12. That's much small, tiny components they are looking on. So when the size of these transistors becomes lesser and lesser, automatically the amount of transistors that can be installed on a particular space will be keep on increasing. So because transistor is a basic component to make uh, the logic gates. So because in the next upcoming slides, I'll show how actually this works. The transistors are the basic components which we'll be using in your hard disk, in your motherboards, everywhere, in your chips, everywhere. The transistor is a basic component which will be doing using it. So this is one just graph. You can see I have taken this graph by considering a graphics card. You know that NVIDIA, Radeon, these are all the trendy graphics cards which we'll be using in our computer. So I have just taken an around some 2 3 years data, and we are just looking in with this graph. So along x-axis, I have taken months followed by years. It is ninth month in the year 97. This is the third month in the year 98. This is ninth month in the year 98. Third month in the year 99. So on. So from 97 to 2003, I have taken the data, and along y-axis, it is telling the number of transistor. And please remember, it is not a 10 number; it is in millions. 10 millions, 20 millions, 30 million, 40 million, so on. So initially, the in the September 97, there was a card, Riva 128, which was having 3 million transistors. Later on, uh, it got increased to in the same size. It got increased to around 7 million. Later on, it got increased to 10 million by the time by around third month of 99. See, in third month of this is ninth month of 97. This is third month of 99. This is 3 million. By this time, it is 10 million. So you can see within 2 years, almost 1.5 2 years, we are able to place 10 millions of transistor in that small chip or in that small card. Later on, the number of transistors got increased. Again, they got increased. Again, they got increased. Later on, NVIDIA different series came into picture. So NVIDIA GeForce 3, which was having 57 billions. So in later on, in NVIDIA GeForce 4, it was 63 million, and ATI Radeon, it was 60 million. So in around 2002, there was ATI Radeon Pro, 110 million transistors were placed in that small chip. And in later on, around 2003, March 2003, NVIDIA GeForce FX 5800, there was 125 million transistor. Just imagine. So the compact, how the compactness is increasing. So that means compactness you are getting. Uh, Initially, we are having 3 millions. In the same 3 million space, now we are in 2003, they were able to place 125 million. Because of this, the compactness of the system is keep on increasing. Next, coming back to the computer components. So the computer components mainly deals here. It has mainly classification as a processor, memory, mechanism. These are the three pieces. When you talk about a computer, these are the three pieces we have to talk about more, or we need to know. So processor, it is to interpret and execute programs. We call it as a brain of a computer. Memory, to store both the data and program. Mechanism, this is very important for transferring data to and from the outside world. So through ports, what kind of ports you'll be using, what version of ports you'll be using, or whether it is serially transmitted or whether it is parallelly transmitted, like that. So let us see an example. So this is just an example of an obsolete computer. Hope you know obsolete means someone which is not used. So they want to sell. So there was an advertisement like this for sale, and it is very cheap. So now, very cheap means someone wants to buy this, and they have given all these descriptions: Pentium, 4.2 gigahertz, all those things. This they have given. So first, you should know what does this each of them mean. Instead of without knowing these things, he cannot purchase it because he'll be having some application in his mind. He'll be working on something, so he might be just for browsing, or he might be you might be working for a clerical post or clerical work. He'll be doing just typing something or just accessing mails, or some calculations he might be, or some he might be an engineer who will be coding. So so before purchasing this computer, he should know whether the descriptions are its whatever the configuration given matches him or not. So being a bachelor of computer application students, if someone asks you, oh, this is an advertisement I have got, can you please tell what is this mean? You should know this. Okay, that's my intention. I want you to know these things. So, what is this L1 cache? What is this PCI? What is this MB? What is this USB? What is this megahertz? See, we are very familiar with MB. Usually, when it comes to computer purchase or anything, we tell what is the hard disk you're having, what is the RAM size you're having. Uh, these are the main things we mainly concentrate. But apart from that, there are many things that we usually will not be knowing also. So let us try to know this. So before that, let us see uh, the units that whichever been used in this advertisement. Hertz. So what is this hertz? So hertz is a unit of frequency. Hope you know that. So clock cycles per second. How many clock cycles per second will be having? If it is 1 megahertz, so mega means 10 to the power of 6. So that many hertz, that many clock cycles will be having frequency. Processor speed are measured in megahertz or gigahertz. So now it is in terms of gigahertz. Byte, it is a unit of storage. So they based on that only we tell gigabyte, terabyte, and all. So 1 KB is nothing but 10 to the power of 2 to the power of 10. It is 1024 bytes. That many number of bytes will be having. Further bytes, the next lower level of bytes is bits. So 1 MB means it will be containing 2 to the power of 20 bytes. Main memory, that is RAM, is measured in MB. So, and disk storage in is measured in GB for small system, TB for large system, and now you know the TB is normal. What we expect now, everyone are purchasing on terabytes. So that configuration everyone looking on for. So now large main memory capacity means you can run large program with a greater speed. That's why you should have large main memory. I was telling here, main memory RAM is measured in MB. So that if it is large main memory, if it is having large main memory capacity, so you can run larger programs, bigger program with a greater speed. So execution speed will be more than having a smaller memory computers. That is what the how higher end systems get differentiated from a lower end system. The lower end systems, they take a lot of time to execute a particular program, but the higher end system, they execute the program very fast because their capacity is more in terms of RAM. So it is random access memory. So the time to access the contents is independent of its location. So it is not dependent upon location where actually it is. The next is cache. So cache is a temporary memory that can be accessed faster than RAM. So always when running a program, everything cannot be stored in the main memory. So they'll be storing in cache memory and they'll be running to fetch the information very fastly or to increase the execution speed of a program. So temporarily the data will be stored in this cache. So cache is also very important parameter that we need to consider. Cache memory is also very important thing. Now let us see. We'll go in detail with this advertisement. So what they have given. So this system has 256 MB synchronous RAM, SD RAM. So they have given like that. So now DDR, SDRAM, they're given. We know only RAM. What is RAM? Random access memory. Yes, every system will be having RAM. Every embedded system will be having RAM. Fine. But what is this SDRAM, synchronous dynamic RAM? So if you know uh, this SDRAM, only dynamic RAM or synchronous dynamic RAM, it is good to know these things. So synchronous dynamic RAM means here the entire memory will be divided into number of divisions. So pipelining will happen. Pipelining, you know that pipelining executing or fetching the information parallelly, continuously. So because of subdivision, making the memory into number of subdivisions, the pipelining will be used in this SDRAM. When a pipeline is used, automatically what happens? The speed will be more. So that is why we prefer SDRAM. Next, And there are, when we see this advertisement, there are 32 kb L1 cache, 256 kb L2 cache. So there are two levels of cache memory. So where L1 cache is smaller and probably it is faster than L2 cache. So these cache are usually measured in KB because they are temporary memory storage units. So we'll be measuring them in terms of KB only. No need of measuring them in, or no need of a huge cache. Next, hard disk. That is main thing we talk about. What is your hard disk? 500 GB, 1 terabyte, 2 terabyte, like that. So 80 GB hard disk. So it determines the amount of data and size of the program you can store. So that is 80 GB. So serial ATA hard drive. So and 7200 RPM. So this is one 80 GB hard disk, and it is having 7200 RPM. That is the rotational speed of the disk. And the faster the disk rotates, the faster it will deliver the data, because after processing, the data will be stored in the main hard disk. So if you want to fetch that information again to the RAM for processing purpose, it can deliver that data to the RAM if the rotational speed of the disk is more. That is rotation for RPM, rotation speed, RPM. It is measured, rotational speed is measured in terms of RPM. So 7200 RPM it is having. Now it can deliver more. Now the question is, what is this ATA? That we next will see. So ATA stands for Advanced Technology Attachment. So this advanced technology attachment, so here it is going to have an uh, integration between the controller directly on the drive itself. So drive controller will be integrated. So because of this integration, what happens? The data will be fetched very fastly. So serial ATA we are having, in the same way we are having uh, parallel ATA. We call it as PATA. This is known as SATA. So see, PATA was parallel advanced technology attachment, which was previously used. But when serial ATA was came into picture, so the PATA was not used. The parallel ATA hard drive was, nowadays we are not using that. So serial ATA we are using, because the interconnection between the hardware and the hardware and the controller, drive controller, is easy, and it is at the same place. Next, it is showing 48x CD read write drive. So CD can store about 650 MB of data, and this drive supports rewritable CDs. And CD drive with rewritable, that means it is having a drive through which we can write the CD. This can be written many times, and the speed of this writing is 48x. Next, 8 USB ports, one serial port, one parallel port. So this shows that there are 10 ports in the system. Why we use these ports? See, ports mainly allow the movement of data between the system and its external device. So to connect your pen drives, to connect your the mouse or keyboard, anything, you need these ports. So this is the place where you are going to exchange the information to the external devices from the system. So serial port sends the data as series of pulses along one or two data lines. One by one will go. It will be just like a queuing system. Parallel ports send the data in a single pulse along at least 8 data lines. It is just like having a single counter, and many of them are looking to get the tickets in a single counter. There are 8 people, they want to get a ticket, and there is a single counter. So one by one goes to the counter and they'll be collecting the tickets. The parallel ports means there are 8 counters, 8 people go to 8 different counters and they'll collect the tickets. So this is the series ports and parallel ports difference. The USB, Universal Serial Bus, it's an intelligent serial interface that is self-configuring. So it supports plug and play options. So this is what we are using today, USB, Universal Serial Bus. Next, coming back to our advertisement. So system buses can be augmented by dedicated I/O buses, input-output buses like PCI, peripheral component interface, is one such bus. Next, this system has three PCI. Such peripheral buses are of three, and it is having a video card, sound card, and data and fax modem. These are the three peripheral component interfaces we are having. So by using the video card, sound card, and data or fax modem, modulator and demodulator modem means which is used for the purpose of faxing or interconnect for getting internet connection for that. Next is coming to the monitor. It is 19-inch monitor. So number of times per second that image on the monitor is repainted is its refresh rate. So how many times it will appear, that is the refresh rate. So the dot pitch of the monitor tells how clear the image is. So dot pitch means on each point of the image on the screen. So the dot pitch is 0.24 millimeter and refresh rate is 75 hertz. So this indicates that uh, the clarity of the monitor is good. So lesser this dot pitch, more will be the clarity. After that, video card contains memory and programs that supports the monitor. So video card is necessary. Coming to the computer level hierarchy. So till now we have discussed about the basic aspects of the computer. So now computer level hierarchy, how actually the hierarchy will be. To write a complex program, you need to follow an rule or an approach which is known as divide and conquer, where each program module solves a smaller problem. So you have to divide it into different sub programs or sub functions, and you have to execute the smaller problems at this by using smaller programs. That will increase the uh, speed, or the execution also will be done faster. So complex computer systems employ a similar technique through a series of virtual machine layers. To use this divide and conquer approach, or to implement this divide and conquer approach, so complex computer system, there will be a virtual layers. There will be different layers. We assume it like that. So there will be different layer. Each layer will be doing different tasks, so that the execution moves on smoothly. So this is one very good picture which tells you. See, I was telling you there is while at the beginning of the talk, uh, there is the hardware and software both needs to be integrated. Why this integration is necessary is, see, at the bottom what we have a logic gates. These are all logic gates which comes under again under electronics. So which is an hardware. So whatever we do here, whatever application we run here, whatever application program, everything we do here, so finally that has to be executed at the chip level. At the chip level means in the chip we'll be having a lot of gates. You can see NOT gate, AND gate. It is a circuitry. So this is the level of hierarchy which uh, is being followed in the computer system. So here in this, the first there are totally 7 levels. So the we this is just for our understanding purpose. Actually, the process flow is like this, but this is an virtual machine layers. We tell there are 7 layers. We tell, but we cannot see these layers inside the computer. Someone you cannot ask. Anyone, or show me the 7 layers inside the system. It is not like that. It's a theoretical concept, but this is the flow, actually, how it happens. So each virtual machine layer is an abstraction of level below it. So in the level 6, we are at the level 6. See, this fellow is going to do something. Is going to um, do some application in his computer. So he's going to execute these programs. So at the user. So in order to do this, the lower level has to support this. So in level 5, we are having high level language, which is been done, which is usually C++, Java, Fortran, etc. These are all the high level languages we are having. Again, in level 4, we are having assembly languages, assembly code. And in level 3, we are having system software, OS, operating system or library code. The users, this application layer has to be supported by this high level language. And again, this has to be supported by assembly language. This has to be supported by your system software, that is operating system. And this operating system has to be supported by the machine. So machine language means instruction set architecture comes into picture. So in order to support this, you need a controller, so which will be a microcode or a hardware. And in order to have this, you need level 0, which is a digital logic, which contains the circuits, gates, etc. So starting from level 6 to level 0, each one of them has to coordinate with each other for the successful execution of the application. So he wants to execute some application here means it has to be executed at the level 0. So this is the hierarchy level we are having. So ultimately the computer circuits has to carry out the work. Whatever you are coding here, that has to be carried out by the circuit system. So let us see what this each level will do. In the level 6, the user level, the program execution and user interface level. This is the highest level we are having. So this is where actually a user is open to. He'll be seeing it. Now we are using an application, StreamYard. So that is an application which we can see. So that is level 6. So which is more familiar? That is what we are seeing. Then to the back end of this, we are having high level language. The level with which we interact when we write programs in language such as C, Pascal, Lisp, Java. So these are all the backend programs which run, the programs which run behind this software or behind this application. To write that application, we'll be using high level language that has to run to execute this application, what we are seeing now. Next, behind that, an assembly language level will come. So it acts as an assembly language produced from level 5, as well as instruction program directly at this level. The programming language and machine language, machine language means the language which is understood by the machine, zeros and ones. So we have to convert the programming language, the instructions what we use, to the machine language, zeros and ones. So we cannot code it in zeros and ones. That's why we will use this hierarchy and keep on converting them. So in level from level 4 to level 3, we are having system software level. So this controls the executing process of the system and protect the system resources. And it acts like a pool of resources. Whenever a particular system requires some resource during that time, it will be using it will be the OS has to supply the necessary resource. It has to supply the necessary resource. So for that purpose, the OS is necessary. The controls the executing process on the system, protects the system resources. Assembly language instructions often pass through level 3 without modification. So there will be no modification. It is just going to process whatever you are going to code. Coming to machine level, So this is where instruction set architecture comes into picture. So consists of instructions that are particular to architecture of a machine. Programs written in machine language needs no compilers, interpreters, or assemblers. Coming to level one, so it is control level. So it contains a control unit which decodes and executes the instruction and moves the data to the system. So this is where conversion happens to the, because you have seen in that figure, finally it is going to the logic circuits. Logic circuits, the gates. Gates understands only zeros and ones. It doesn't understand ABCD also. So we have to convert this programs, whatever we have done. So we have to decode it, and we have even the instructions also, and we have to give it to the control units. So the microprogram is a program written in low level language that is implemented by the hardware. So the hardware, whatever the hardware can implement, so to that will that program will be converted by this control level. And hardware control units consist of hardware that directly executes machine instruction. Lastly, we are having digital logic level. So this digital logic level, in this level, we find digital circuits, mainly the chips, which contains inbuilt transistors, gates, all those things. So digital circuit consists of gates, wires, and all. This component implement the mathematical logic of all other levels. See, while writing a program, we will have a logic. Finally, that logic has to run. That has to success. Then, so in order to implement that logic, we integrate it with this level 0. So that logic will be executed. Then your program will be succeeded. So this is what the overview of the computer organization and architecture, or a brief introduction I have. So at last, I just want to talk 1 or 2 minutes about the career, and I'll be closing it. So even I work as a placement officer for BMS college. So I just want to give you some hints. So because since you are in third semester, so you have some time to prepare yourself. So usually I follow some strategies for my students to get them placed in the companies. So in that strategies, this is a pyramid structure of competency development which I follow. So when starting from the first year or second year, uh, I'll start with this kind of strategy for them. Even you can try to use this strategy to get employed. Where before going out, you'll be having an offer letter in your hand. So first thing, what you should do is, first thing is training. Uh, if the college is giving you a training, it's well and good. Otherwise, you can take any online trainings which is related to aptitude knowledge, logic reasoning, English knowledge, and all. And mainly, you can do self learning. See, a lot of stuffs are available online, so you can do self learning and you can acquire this basic things, aptitude, just to crack the first level. After that, we are having, you need to have domain knowledge. That is where the subject knowledge will come into picture. So where curriculum and PBL will be attached. So curriculum means the syllabus, what you study. You should be well versed in that. So whatever you have studied, you should know it properly. PBL means do some projects, problem based learning. PBL means to do some small projects related to the subjects, take up small problems and try to solve it. uh, that gives you enough knowledge, and you can claim that in your resume. Later on, take up some employability test. There are a lot of employability test givers like CoCubes, we have AMCAT, we have, and sometimes even the colleges will have in-house assessments. This CoCubes or AMCAT, they'll not train you, but they'll give you employability test, and based upon the scores, they'll directly link you to the companies. So this is what you can do. So if you are passing through this, the final will be a graduates with employment. So this is the pyramid structure of competency development, which you can try to incorporate now only. So in next 1.5 years, you'll be having your job offer in your hand. So that's about my presentation. So if you need any help, you can contact me through this mail. So I'm done with my presentation. Thank you for your patience listening.
Um, Thank you. Uh, Thank you, Mr. Raghunandan, for your uh, valuable information. Now, I would like to express my heartfelt gratitude to the speaker, Mr. Raghunandan GH, for accepting our invitation in spite of his busy schedule and for sharing his valuable knowledge with our students. Thank you, Mr. Raghunandan.
Thank you, Swati.
I would also like to thank all of our students who sincerely committed to this event to make it a success. This event would have been impossible without the support of each and everyone present over here. And I would also like to thank our faculty members who has joined this virtual session. Okay, so I ensure that this seminar is profitable and fruitful for everyone present over here. Thank you. Thank you for joining us. Again, thanks, Mr. Raghunandan, for providing your valuable information.
Thanks for inviting me for the session. Thank you once again.
Okay, thank you.